Hello everyone, I'm Khurram Soomro, and today I'll be presenting our work from CVPR2016. The paper is called Predicting the Where and What of Actors and Actions through Online Action Localization. This work is jointly co-authored with Harun Idris and my advisor Dr. Mubarak Shah. So first I would like to define the problem. In this paper we want to predict where the action is happening and what the action is. So here I'm showing video of our method. On the left, I'm showing video frames of a testing video in which the localization of the action is shown by the yellow bounding box. On the right, we have the list of possible actions which have been sorted by the prediction score given by a classifier. So I'll run this video, and here the action that is being performed is kicking a ball, and you'll observe how the prediction score varies with time. So as you can see, when we observed or when we were streaming this video, the prediction score improved as we get more information and we are viewing the entire complete action. This problem is what we call online action localization. To define it in a better visual manner, here I'm showing the frames that we are viewing in a streaming video. The problem of online action localization tries to simultaneously predict what the action is and detect it in each frame, as shown over here. Now compared to this, traditionally when you're given a video, offline action localization methods would try to detect the action by putting a bounding box in each frame and then recognize it by assigning it a label. In this proposed paper, idea is that we want to simultaneously detect and predict the action, and here we present a novel approach for the problem of online action localization in a streaming video. I would like to highlight the differences between offline and online action localization. So in offline, you have the entire video available for recognizing the action as well as detecting it, as compared to online where we're looking at partially observed video. In offline, you have the entire motion of action visible because you have the entire video present in front of you. As compared to online, you have limited motion information, so it's more challenging. Hence, it becomes a recognition versus a prediction problem. In terms of detection, you can use all the frames for offline action localization. However, in online, you have to detect frame by frame. Hence, it's more difficult, more challenging. The key idea in our paper is that we want to distinguish the foreground actor from the background. So there could be a number of ways to do that. For example, you can apply human detection in each frame, or you can segment. Now, there are ways to do segmentation. You can do object segmentation. You can segment based on motion. Or more recently, people have tried using action proposals. You can also use pose estimation, which means you are trying to detect the human body joints to find where the actor is. In our case, we use pose estimation as well as segmentation together to do online action localization. In our proposed framework, given an input stream of video frames, our goal is to predict and detect the action in the current frame, T, as shown over here. We perform or apply our approach in a batch of frames. So given, let's say, delta frames, from T minus delta to T frames, we'll apply our method to predict what the action is and where it's happening. Now, given these input stream of video frames, in each frame we also extract superpixels as well as estimate pose. The framework of our online action localization method is based on 3 components. First, we want to generate a foreground likelihood based on superpixels. Our second component uses poses, and combined, our goal is to locate where the action is at Tth frame, which is represented by a bounding box xt. Now, because it's a video, you have to localize frame to frame. We generate or we use a state transition model, and together we combine these 3 components in a Bayes rule formulation such as shown over here. Here we're trying to predict or estimate the probability of an actor by a bounding box given all the superpixels st and poses pt. And the state transition model in this rule is assumed to be Gaussian distributed. Right. Now, for the first component, which is the superpixel-based foreground likelihood, we use the pose bounding box as well as superpixels to learn an appearance model by clustering these superpixels in each frame. With the way we clusters, we apply just simple k-means. And for each cluster, we assign a confidence based on its overlap with the foreground action, which is detected by the yellow bounding box. Once you've learned this appearance model, we generate a score for each superpixel, such as shown over here. And this is what we call superpixel-based foreground likelihood. The way we calculate this foreground likelihood is that we compute the distance between the color feature vector of each superpixel with the centroid of the cluster, as well as the optical flow. We update the appearance model every fifth frame to avoid visual drift while we are localizing the action as we go. Our second component is pose-based foreground likelihood, which uses poses to find out where the actor is. Now, because these are action videos, it is quite challenging to correctly estimate the pose because of high articulation of human body. And that's why we want to refine these poses by imposing certain smoothness constraints. For that, we use appearance of joints, location, as well as scale of the pose. The way that we impose this constraint is by fitting a spline trajectory through each joint location of every pose in a batch of delta frames. Once we fit these trajectories, we want to refine these poses by assigning or recomputing the score for each pose in a batch of frames. For that, we define this cost function, which involves the raw score given by the underlying pose estimator, a new smoothness cost, which is based on appearance of joints, location of joints, as well as the scale of the pose. Combined, we try to minimize this cost function to get new poses in an iterative manner, such as shown over here, given by P star. Now, for our first constraint, which is appearance smoothness of joints, here I'm showing the pose estimated in a batch of delta frames, as well as the superpixel-based foreground likelihood overlap with the poses. Our task over here is that we want the appearance of the joints to be similar across frames. So the appearance here is the foreground likelihood score generated by the overlapping superpixel for each joint, and we want them to be as close as possible between consecutive frames. Our second constraint is based on location smoothness of joints. So here, since we have fitted spline through each joint location, we want the spline location in each frame to be as close as possible to the location of the joint. We want to minimize this so that we have smooth movement of joints in each frame. Lastly, we have the scale smoothness of joints, which says that the height or the scale of the bounding box for each pose should be smooth across frames. So here I'm showing a bounding box containing the pose and a bounding box which contains the location of the joint trajectories. We want them to be as close as possible. Using this minimization, we are able to get better poses. Here I'm showing some qualitative results of our method. So these are the poses estimate before we apply our approach. On the left, I'm showing the action called kicking. On the right, we have walking. And as you can see that there is some error in pose estimation. After we apply our method, we are able to better localize joints. And you can see on the left, we are able to localize the arm correctly, and we are able to localize the head correctly in the right action. Here are some more results where we have kicking, action, and picking. And once we refine the poses, we are able to get better joint localization, for example, the leg in the left as well as the right. Now, once we have the foreground likelihoods estimated from poses as well as superpixels, we construct a spatiotemporal graph in which nodes represent superpixels and edges are between spatiotemporal neighbors within the frame as well as across frames. Once we have this spatiotemporal graph, we apply CRF, conditional random field, to get fine action contours such as shown over here. In this, our unary potential is given by superpixel and pose-based foreground likelihood, and the binary potential comes from similarity of color as well as motion between superpixels. We formulate the CRF as shown over here, where we have one unary potential and two binary potential, which represents the spatial smoothness as well as temporal smoothness. The unary cost comes from foreground likelihood from pose and superpixel, and the spatial binary potential includes color histogram, histogram of flow, mean color, motion boundary, and edges between superpixels. Our temporal binary potential includes color histogram, histogram of flow, as well as color mean. Now, once you've localized the action, as you saw using those fine contours, we also want to predict what the action is. So for that, we use SVM, and this contains two parts. First is the training part. So given a number of training videos, let's say for an action called kicking, here I'm showing these videos along with their ground truth shown by the green bounding box. We divide these videos into temporal segments of 1 second each. So going from 0 to 1, 1 to 2, and so on, and learn an SVM on each temporal segment for 1 second, 2 seconds, and so on. Now, at the time of prediction in our testing video, we estimate the prediction score for each action as shown over here. And for that, we use dynamic programming, which accumulates confidences by matching sequences from training to testing videos. For features, we use improved dense trajectory features, as well as post features, which includes the normalized joint locations, the relative joint locations, the angle between joints, and their orientations. Here's a summary of our proposed approach, which goes from an input stream of video frames towards predicting what the action is, as well as localizing them in each frame. For experimental setup, these are the features that we use. So for SuperPixel, we use the slick method. For pose estimation, we use Yang and Ramanen's method. We use improved dense trajectories as well as pose features. For evaluation metrics, we use the standard way of measuring the action localization, which is the ROC curves, receiver operator characteristic, as well as the area under the ROC curve. However, we introduced two new metrics, which analyzes how the prediction accuracy varies with time as a percentage of the observed video. We also want to analyze how the localization performance varies with time, given by the area under curve against video observation percentage. We also generate a baseline in an online manner where we exhaustively generate bounding boxes in each frame and then connect them based on their appearance similarity. For the datasets that we use are two. So we have GHMDB dataset, which consists of 21 actions and 928 videos, as well as UCF Sports, which contains 10 actions and 150 videos. So here I'm showing some qualitative results. We're trying to predict the action. On the left, we have the foreground likelihood score from Pose and SuperPixels. In the middle, we have the testing video frames and the action given by the yellow bounding box. And finally, on the right, we have the sorted prediction scores for each action. And here, the action is kicking a ball, and you'll see how the prediction improves with time. So you might have observed that in this case, we are able to predict the action well before the video ends. So even with a few frames, we are able to correctly predict. That helps due to using pose features as well as dense trajectories. Here's another example. The action is catching, and you'll see that initially the prediction score was very low right at the bottom, but as you view the video, we are able to correctly predict, and we're getting a higher score for that. Here are some qualitative results where we are showing our action localization results given by the yellow contour and comparing it with ground truth shown by the green bounding box. So these are from GHMDB, which consists of pushing, sitting, throw, and so on. Here are some more results from UCF Sports, which consist of swing bench, walking, running. Here you can observe that we are able to localize multiple actions simultaneously. Now, these were qualitative. We also want to quantitatively analyze our online action localization. So first, we want to see how our prediction varies with time. So for that, we plot this graph which shows the prediction accuracy as a function of observed video percentage, which says that if you observe 20% of the video or 40% until the entire video, 100%, how does this accuracy change with time? So here I'm showing results for GHMDB, and as you can see, the prediction accuracy improves as you observe more video. And here are the results for UCF Sports. So you can see that GHMDB is more challenging as compared to UCF Sports, and we are able to improve the results with time. Now, these were the prediction accuracy for the entire data set. However, we also want to analyze how each one of those actions varies with time. So here I'm showing the similar results for each action. So these are from GHMDB. The action here we're looking at is brush here. And you can see initially we have a prediction accuracy of about 20%, and which goes until 60% when we've viewed the entire video. Here are some more actions: catch, clap, and the remaining ones. So we have a total of 21 actions, and you can see for each action we are able to improve the prediction accuracy as you observe the entire video. Now, once you've looked at it individually for each action, we want to analyze it by saying which actions are more challenging as compared to the others. So we sort the action based on the area under the curve of this plot, and we see that for JHMDB, pull-up action is more easier to predict as compared to jumping action, which might have larger pose variation and could be more challenging. We analyze this in a similar way for UCF sports data sets, where kicking is easier as compared to swing side, which has large motion variation as well as poses. Now, this analyzed how the prediction accuracy varies with time, but we saw that for some actions we are able to predict well before the video ends, maybe half a video or less than that. So we want to analyze how early we can predict each one of those actions. So for that, we set a prediction accuracy of 30%, and we would like to analyze which ones are easier to predict and how much percentage of the video do we need to observe to correctly predict the action. So here are the results from JHMDB, which shows that for pull-up action, we only need to watch 14% of the video, and we are able to get more than 30% accuracy as compared to swing baseball, which needs about 70% video percentage viewing. You might have observed that for some actions we don't have any numbers, which says that these actions didn't even reach an accuracy prediction of 30% even after viewing the entire video, which shows the challenging nature of this problem and this data set. Here are some results from UCF Sports, where for kicking action you only need to view 1% of the video, which is hardly a few frames, and you're able to correctly predict the action. However, for our swing side, you need about more than 60% video to be seen in order to correctly predict the action. Similarly, we also want to analyze how the localization performance varies with time. So for that, as I mentioned, we use area under curve. So here we have the area under curve as a function of video per observation percentage. So here I'm showing the curve at 10% overlap with the ground truth. And we see that we improve the localization performance with time. However, we also want to analyze at different overlap thresholds. So here we have an overlap threshold going from 10% with the ground truth until 60%. We analyze this localization performance for UCF Sports as shown on the right. Now, these were the prediction and localization performance against time. However, we also wanted to analyze how we do against the traditional offline action localization methods. So for that, we did experiments on UCF Sports. On the right, we have the ROC curve, which is true positive rate against false positive rate. Here I'm showing the state-of-the-art methods for UCF Sports. We computed a baseline in an online manner, shown by the gray curve, which shows the challenging nature of this problem. And for our method, we are getting much better results and competitive to the state-of-the-art. In certain cases, we are even performing better than offline action localization methods. Now, this ROC curve is plotted as at 20% overlap threshold with the ground truth. We also want to analyze this against multiple overlap thresholds, such as shown over here, which goes from 10% to 60%. In conclusion, we introduced a new problem of online action localization, which simultaneously predicts and detects the action. We proposed a new approach which uses poses in combination with superpixels to get a foreground likelihood score. We inferred the action location using conditional random field, such as shown earlier, and we provide a detailed analysis of how the prediction varies with time as well as localization. Thank you.